Today, we're going to continue looking at gradients and directional derivatives. Let's suppose that we have a function, f of xy. Now notice that f of xy is a scalar function. It takes as an input scalars x and y, and it outputs a scalar z, or f at xy. But we're going to make a vector out of it. So we're going to make a vector, the gradient of f. It's going to be the x derivative times I plus the y derivative times j. Such a simple thing to construct, and yet it tells us such an important piece of information. It tells us the direction of maximum increase of the function at a particular point. If we want to know what's steep, which way is steepest, the gradient tells us that. Graphically, we'll see that the gradient is perpendicular to the contour at the point. This makes sense. The direction of maximum increase should be perpendicular to the direction of no increase. So tangent to the contour is no increase. And I know I've drawn this picture multiple times, but it bears repeating. If we've got a contour, cruising along the contour, this is where the function is constant. So if we're running tangent to the contour, so the contour is where the function is constant. So if we're running tangent to the contour, if we're running along the contour, there's no change. The function, the value of the function is not changing. That's how we built the contour in the first place. The gradient will be perpendicular to the contour. And that's going to be the direction of maximum increase. This makes sense because if we look at we're making the directional derivative, the dot product of the gradient and a unit vector in the direction that we might care about. So the unit vector can be anywhere. So if we have a unit vector going in this direction, how is the function changing in this direction? Defined by a unit vector. Take a look at how we're calculating this directional derivative. We're using the dot product of the gradients and the direction we care about. So remember that the other way we calculate the dot product is to take the magnitude of one vector times the magnitude of the unit vector, which will just be 1, times the cosine of the angle between the vectors. So we know that the directional derivative tangent to the contour is going to be 0. And so the cosine, so if the angle between the direction we're traveling and where we know the change to be 0 is 90 degrees, cosine of 90 degrees is equal to 1. Oh, sorry, I switched back over to trigonometry. Cosine of pi over 2 is equal to 1. And so that's going to be that's how we get the maximum value of cosine of theta. If the angle between the gradient and the directional derivative is 0, that means the directional derivative is 0. Oh, sorry, 1. I think I just said that completely backwards. I don't know if this is a more coffee problem or a less coffee problem, but I know what I'm going to apply. So let me try again. We know that cosine of 0 is equal to 1, and the cosine of 90 is equal to 0. So if the angle between the gradients and the direction we care about is 90 degrees, the directional derivative will be 0. if the angle between the gradient and the direction we care about is 0 degrees, then cosine is equal to the cosine will be equal to 1, and that will be the maximum value of the directional derivative. We didn't choose to use cosine instead of sine. Cosine is the one that works. It has to do with the adjacentness. So when cosine is 0, the angle between the gradient and the direction is 0 degrees. That will give us the maximum value of the directional derivative. When cosine is 90 degrees, then the direction is perpendicular to the gradient. And we know that's the tangent. And along the contour, there's no change in the function. So the dot product is making double sense. All right, I've had a request for a problem from the homework, which I'd like to do, which is perfect timing for this particular question. But before we do that problem, I want to remind us about how we use local linearity and changes in F. So let's suppose that f of 3 is equal to 5. And let's further suppose that f prime of 3 is equal to -2. We know the value of a function at a point, and we know the direction that the function is headed at that point. We know the derivative at that point. We can use this information to approximate f of, say, 3.1, something close to the value of 3. And what we're going to do is use the tangent line. So we're going to bring up the tangent line. Y is equal to, we'll start off at 5, and we'll subtract 2 whenever x moves off of 3, when we're x units away from 3. So if we evaluate the tangent line when x is 3.1, that'll give us an approximation. So we're going to plug the 3.1 in for the x. So we'll take 5 minus 2 times 0.1. The 3 wasn't really important. The change from 3 to 3.1, that's what we cared about. Remember that the -2 is the rate of change of y with respect to x. So the -2 is delta y over delta x. And the 0.1 is the delta x. So the delta y times the delta x, when I multiply f prime times the delta x, I get the change in y. So the delta x cancels out, and the minus 0.2 is my delta y. So we started off at 5 when x is 3, and it dropped by approximately 0.2 when x moves to 3.1. This is just using local linearity. I didn't subtract the whole 2 because that's how much f changes when x increases by 1. So -2 is how much f changes when x increases by 1. So I wanted to scale that down because it was only a difference of 0.1. So let's take a different set of given information. Let's suppose that P let's suppose that F at 5, 6 is equal to 15, and F at 5.03 and 5.96 is equal to 24. That's a lot of change for a small step. We can use this information to approximate the directional derivative at P in the direction of Q. So I've got P, and I've got this point Q, and we're asking how much is the function changing? Red was for the gradient. How much will the function change when we go from P to Q? So, I'm about to knock stuff over here. All we need to do to see how much the function changes, to approximate how the function changes, to approximate the rate of change of the function, is take how much the function changed divided by how far it went. So the delta F is the change in F it's just going to be the change. We're just going to calculate the change in F divided by the distance in the same way that the derivative is the change in Y divided by the change in X. How much the function changes divided by how far it went. So the change in F, if we go from P to Q, we ended up at 24 and we started off at 15. So we had a change of 24 minus 15, which is 9. Yeah, 10 negative 1. Then we have to calculate the distance that we traveled from P to Q. And so we just need the distance with the distance formula. So the difference in the x's is 5.03 minus 5 squared plus 5.96 minus 6 squared. And then however much that is. So whatever you get for that value, 9 divided by that is what we are looking for. Any questions? How's everybody okay? Cool. It's funny because the video has my audio and I'm responding to like text. So it's just kind of me talking to myself. Then again, I can't actually confirm or deny that I'm actually just talking to myself. Maybe this is just my perception and I'm, locked away somewhere in a padded cell or hooked up to a machine and this is the matrix. So distance formula is, the question is, how does the distance formula relates to displacement? The distance that we want here is just the displacement. I want the displacement between the 2 points, which is the same as the distance between the 2 points in this case. We make a distinction between distance and displacement. So if I drive to school and back, my displacement is 0, but my distance will be about 10 miles. So the distance traveled is 10 miles because I went there and back, but my displacement would be 0. In this case, we're going from one point to another point. I go from one point to another point, and so my displacement and my distance are the same. We're not worried about going in other directions. We're just going in one direction. So I have another message, the homework problem, but it seems to be incorrect. Let me check. Let's see. So mine says this one should have been, let me check my calculations real quick. This will be some exciting YouTubes. Oh, minus. And then 24 minus 15 is 9. So this delivered me a 180, and that's what my problem wanted. It wanted 180. So oh man, look how I did this calculation. Look at this. It's 3, and there's a 4. I should have known it was going to be 5. I'm going to refresh the problem. Hang on a second. All right, points to Wiley for this one. This other one has a point of P is 6.5 and Q is 6.03 and 4.96. So they just use a 3, 4, 5 triangle. That's clever. Points to Wiley for that one. So I'm not sure why an incorrect is coming up. And I think the problem is changing values. So if you're getting an incorrect and you follow this method, then send me a screenshot and then we can try to sort it out. Calculator fight scene montage. Need some Karate Kid music there when this is playing. All right. So there was another question. I had some email questions about the problems that had graphs on them. So just, I can't remember which one specifically, but if we're looking at a graph or a contour diagram, so I'm going to make it easy on myself because it's early. So let's suppose that we have these contours on a graph, and let's say that we got the 50, and then 48, and then what did I subtract? 2, 46, and then 44. If we have a point here, P, we can see the direction of the gradient. The gradient is going to be the direction of maximum increase, and it will be perpendicular to the contour. So in this case, I'm going to draw perpendicular to the contour, and I want to go in the direction of maximum increase. So the gradient should point from 46 towards the 48. So for those problems, that's what you're looking for. You want the gradient to be perpendicular to the contour and in the direction of maximum increase. The direction of maximum decrease will just be the opposite of the gradient, minus gradient. Log gradient. All right, so there was another question. This is also exciting YouTube, where off camera I'm pulling up different problems. All right, so the other question comes from 14.5. So here we need to be talking about gradients in space. So here, when we're looking at gradients in the plane, we know we have a surface, but we're just looking at where the inputs are. So remember, these contour lines represent some surface that's well above the XY plane. So I drew a bunch of boring parallel lines. So this is some kind of plane sloping down from down here, and then it slopes up. So that we hit 50 up at this line right here. And the gradient is just marking the steepest ascent up that plane. So we're going, oops, I can't do it now. So we're pointing up as we go from down here on the paper out towards the camera. I don't have 3D camera, so I wouldn't know what to do with it anyway. So remember, the gradient is just sitting in the XY plane. The gradient is kind of taking the place of the delta x when we're looking at a function of one variable. We're just looking at what the input's doing down here. So here's our gradient is in the plane, even though it's pointing a direction that we're going to use to determine stuff about the surface that is above this plane. So when we have gradients in space, you could probably figure what we're going to do next. We go from gradients in the plane, R2, to gradients in space, R3. So we'll be looking at a function of 3 variables. Let's say W is equal to f of x, y, and z. As this book is rejecting the wisdom of x1, x2, x3, and x4. So when we look at the function W is equal to f of x, y, and z, we're now talking about a 3-dimensional solid in 4-dimensional space. So this is an upgrade from our function of 2 variables. Remember, our function of 2 variables, f of x, y, is a 2-dimensional surface in 3-dimensional space. So if I throw another variable in there, oops, this is z equals. This is in R3 because I've got an x, a y, and a z. W is equal to f of x, y, and z is in R4 because we've got x, y, z, and w. So our graph is going to be a three-dimensional solid in four-dimensional space. We're going to want to make a gradient out of this as well, because I just said this is going to be gradients in space. So it makes sense of gradients, and they're going to be three-dimensional. The good news is it works exactly how you guess it would work. If I want to make the gradient of f, you know what, I'm going to drop these. This is going to take too long to write. The gradient of f, I'm going to have the x derivative in the I direction, the y derivative in the j direction. That was our gradient in the plane, but I've got a gradient in space now. So I'm just going to drop a third term, the z direction, z derivative in the k direction. Just like we would have guessed. Let's talk about, no, there shouldn't be. No, can't use prime notation for our derivatives because there's too many derivatives running around. We can use prime notation when it's a function of one variable. So we can say f prime of x, because there's only one variable to take the derivative with respect to. That sounded really weird. But now we have a function of three variables. So we got three partial derivatives running around. We have the derivative of f with respect to x, the derivative of f with respect to y, and the derivative of f with respect to z. So I can't just use prime notation anymore. Because if I put f prime of x or f prime, people would say, what variable are you taking the derivative with respect to? So I got to put the subscripts of the x, y, and z. So we build the gradient in space exactly the same way we built the gradient in a plane. We just take the partial derivatives for our regular directions, our I, j, and k directions. So what things do we know about this? The gradient of f is going to be the direction of maximum increase. The gradient is still going to tell us the direction of maximum increase. Just like the gradient in the plane, the gradient should tell us the direction of the maximum increase. Otherwise, we shouldn't be calling this the gradient. We should call it something else. It's also going to be perpendicular. It's a vector, so it will be perpendicular to the level surface. Since we have a function of three variables, we don't have contours, which are level curves. We have level surfaces. Everything just goes up one dimension. So we go from z equals f of x, y. It's a two-dimensional surface in R3, and the gradient is perpendicular to the level curves. F of x, y, and z is a three-dimensional solid in four-dimensional space. And so the gradient is perpendicular to the level surfaces. Surfaces are 2D things. Level curves, those are 1D things. Contours are just a particular kind of level curve. This follows our theme of taking old stuff and just making new stuff out of it. It would be horrible if we had to have a completely different set of rules for a gradient in a plane and a gradient in space. Otherwise, we'd have to come up with some kind of different concept. All right, so with regards to the homework problem, hold on, my homework problem is loading. So with regards to the homework problem doesn't give you a function of 3 variables. The homework problem gives you a function of 2 variables. So it says, consider the function, camera. So the homework problem says, consider the function and then it gives you a level surface. Suppose S is the surface. Z equals f of x, y. So the problem is to find a vector normal to the surface. So we need to make a function of 3. We want to make a function of 3 variables so that we can build a gradient in space. So what we're going to do is take z equals f of x, y, and just going to make a function of 3 variables out of it. So we're going to build a function of x, y, and z by just subtracting. So we're going to say f of x, y, z is f at x, y minus z. And since S is the surface, z equals f of x, y, I'm just setting the function to be subtract z from both sides and set it equal to 0. We're looking at the level surface of the function capital F when capital F equals 0. So if I build this function, S is the level surface then we can build a gradient in space. And then we can make our calculations about the other given vector. That is an S. Any questions? All right, this is not the complete solution to the problem, but I did just talk about gradients in space. And like, oh, how come we're talking about gradients in space and then you drop this function of 2 variables on us. And kind of the point of this problem was to take this function of 2 variables and turn it into a function of 3 variables, and then consider a level surface. Then we're into gradient land and all that fun stuff. All right, let's see. I see that I really loaded y'all up with a lot of homework. What was 14? Why did I put all these things? All right, so here's our plan for the weekend. Tomorrow I've got office hours. So if you would like to meet with me at some point tomorrow, between 9 and 11, then make sure to send me an email to make sure I'll be on, and send me an email with a time. So if you just say, I want to meet in office hours between, office hours tomorrow, you'll want to tell me what time you'd like to meet. So if you're like, oh, can we meet at 9 o'clock? Then I'll be on at 9. Can I meet at 9:30? So if you send me a request for office hours, you have to specify a time to make sure that I'll be sitting in front of my computer at that time. But I'll just be opening up the link to my, and I posted that in the announcements, the link to the Zoom. That's just my generic Zoom room. Any questions before we adjourn for the week? All right. In that case, that's all for today. And that's all. Everybody's blurry. That's all for today. And that's all for this week. Everybody have a good weekend. I'll see y'all on Monday. Thanks for playing.